All right. Oh, will you hit the Jake? Will you hit the third button down? Thanks. What was I talking about? Oh, new Bible homework is up. I put it up yesterday, so make sure you give yourself a reminder to have that in by midnight on Sunday. I was surprised that I think 3 of you turned the first weeks in late, like multiple days late, which is just put a reminder. All right, so that should be free. Huh? Sunday. Yeah. It's been like that for a year now. No, at least a semester. I used to do it by the end of the week, and I thought it was just easier to do the catch-all Sunday by midnight. So that allows you to procrastinate even more and then miss the date. It makes you feel worse about it. Like I really had no excuses. I don't know. Okay. So we talked about several of these things last time. Have I given a reading assignment yet? 1 through 5. Good. Well, through 1.5, right? Yeah. Okay, perfect, because that's what we're talking about today. Okay. Yeah, you can get in. There's chapters. There's 5 chapters. We're good. So we talked about at the high level memory hierarchies last time, cache memory, L1, L2. We didn't talk about those in detail, just the idea that the closer you get to the processor, the smaller and the faster and the more expensive per bit the RAM tends to get. All right, and we have to play this game from a computer organization perspective of where do we need RAM to be extra fast versus where do we need memory to be large capacity versus where is it okay somewhere in between. All right, there's this balancing act. All right, this last idea, dependability versus redundancy. I mean, obviously, we want our machines to be as dependable as possible. The thing that kind of comes to mind with this in the computing world has to do with hard drives. How many of you have ever heard of RAID technology as it relates to hard drives? Okay, what is RAID technology? What's it used for?
It's just a way to kind of use multiple drives in a pretty efficient manner.
Okay. Now, RAID can come in a couple, there's different flavors of RAID. For instance, RAID 0 actually allows you to, go ahead.
With RAID 0, say you have a 2 terabyte drive and another 2 terabyte drive, they'll be a copy of each other in case the first one goes out. You can just
that should be RAID 1.
RAID 1 faster one.
I think RAID 0 is when they concatenate. So you have two. If you have 2 2s, you have a 4.
No, I'm pretty sure RAID 0 is the concatenation, and RAID 1 is actually, is RAID 1 the copy, or is it where you have like literally half the block on one, half the block on the other?
Yeah. So RAID level 0 is called striping, where you take, you get twice the performance because you actually have 2 read-write heads on the hard drives, but you get 2, if you have 2 2-terabyte drives, you get a single, logical single 4 terabyte drive. But when you write stuff to it, because things are striped across, evenly balanced across the 2 drives, there's a reasonable chance that when you go to write something and you go to write something else, that it might be able to write both of those things at the same time because it's 2 physically different read-write heads. So that's more geared towards performance as opposed to mirroring, have 2 drives that are actually duplicates to each other, where when you write something to one, that same thing is written to the other, with the idea that if one drive fails, hopefully you don't have 2 drives fail at the same time. And we don't care so much about the details of RAID here. I did hit record. All right, I think we're back on. I'm just fumbling with it, making sure I didn't break the recording. Okay. Yeah, where am I at here? Yeah, so in any case, you know, when we look at hard drive rating, which is kind of an idea of dependability and redundancy, and then related to performance up above, some of these approaches give us faster performance at the cost of, if one drive dies, all of our drives die in RAID 0, where we're striping across multiple drives. So we're basically saying, I'm going to roll the dice here, and I want maximum write performance at the cost of any single mechanical failure means I've lost everything. Now, you have alternate ways of doing it, where basically you have two drives that act as a single drive. So every single time you write one thing, it writes the same thing to two separate drives or even more drives. And then some of these situations allow you, when you get to RAID 3, RAID 5, these allow you to have one or more drive failures and still be able to use the other drives to rebuild the drives that were lost. So that gives you more dependability. You might have downtime of, a half hour or something like that. But, in any case, we have to make that decision about how important is something to be ultimately dependable. I mean, obviously we want our machines to work most of the time, but or more than most of the time, a high percentage of the time, a very high percentage of the time. But we care less about the dependability of our personal laptop than we might care about your bank server or something like that, where we want that to have 100% uptime with no question, where if we have to reboot our laptop every now and then, that's not the end of the world. All right, something like that. So these are things that we need to consider as well. Okay, so that's kind of the global high level of the stuff we're going to be talking about this semester. Now we're going to start talking about the things that live underneath that. Now, a topic, I'm not going to spend too much time on it, that we've talked about before, this idea of what lives below your program, and this is more of an operating system idea here, so we have our hardware. Your computer, the nuts and bolts of your computer, that kind of stuff. And then we ultimately have our application software that sits above that, Microsoft Word, Instant Messenger, whatever it is, whatever applications you're using. Even what we consider to be our operating systems, whether it's Windows 10 or the Mac OS, these are all part of our application software, because typically what we might call an operating system is actually known as a distribution, right? So Windows 10 is the distribution. NT kernel is the actual operating system that lives underneath that distribution. So that's where this layer comes in right here, the system software layer. And several of you had the system software class last semester, the 450 class, where we talked about that guy as being the liaison between the operating system and kind of the underlying hardware. We've even seen some, let me go back. I like this Linux assembly one. So in one of my classes, you've seen this code before, right? So kind of a assembly language, low-level code for saying hello world. This is actually this is related to the memory we talked about last time. So these hardware registers, this is the memory that lives the closest to the CPU, are things like EDX, ECX, EBX, EAX, and we're moving various pieces of information into these little memory buckets. Then we're calling upon our operating system right here to go and process the stuff that's living in these buckets. And one of the things that we're leveraging here is a system call here, syswrite. So this assembly code specifically is assuming that we are using Linux as our operating system, which has a collection of APIs, a collection of system calls that we can leverage. One of them is called syswrite, that knows how to do the magic of getting something displayed on the screen, or getting something displayed here, wherever this file descriptor points to, which is this guy right here. All right, so when we call the kernel is going to say, okay, what do you want to do? I want to syswrite. Where do you want to write it? I want to write to standard output. What do you want to write? This is the data I want to write, and how long is that data? So it knows how far to walk through memory to get to the data. And ultimately, it's going to put it out on the screen. But we are relying on this system call right here to do a lot of that heavy lifting. And that guy lives inside of this system software layer here in this picture. All right. That way we don't have to write the zeros and ones to ultimately do that, but somebody did. The folks that wrote your operating system, that wrote the actual underlying kernel, they used a high-level language like C to write the actual logic, to write something to the to, in this case, standard output, which would be the monitor. And at some level, they probably had to go and write portions of that, at least in assembly code, to teach it exactly how to talk to the hardware. All right, and we even see this if you have built a computer before. You have the latest, greatest $1,000 graphics card, GTX 1080 Ti, whatever. You stick it into your machine before you've installed any drivers or anything like that. Does it work? Will it give you a video output? Sure. So you're saying if you have a computer that you put this brand new graphics card in it, it doesn't give you any video output, you just have to make guesses on where the button might be on the screen to install the driver?
Just the default VGA.
Yeah, default VGA. Yeah, lowest common denominator of what it means to talk to a graphics card. All right, so it's not going to talk to it in all the special ways that card is capable of understanding. That's what that driver teaches it. But it's going to talk to it in a lowest common denominator, that VGA subsystem, which is going to be something that lives inside of system software. It knows how to speak the language of VGA. Okay? So this is kind of a high-level picture of what our computers today look like. You have your hardware, you have your operating system that sits right on top of the hardware, and then we have on top of that what a lot of us would call our operating systems, which are actually the distributions, which are a whole bunch of user applications that allow us to more conveniently interface with the operating system. Make some sense? Okay. Let's see if any other pictures on this one. All right, so we've talked about, we know what binary digits are. We looked at some conversion stuff last time, right? That's not us. This is us. Yeah, so we looked at conversion stuff here to go from bits to bytes to kilobytes to gigabytes, gigabits, all those things. So little b means we're dealing with bits, single zeros and ones. Big B means we're dealing in collections of 8 bytes. So 8 bits is a byte. So make sure you pay close attention to the little b's and the big B's as you go through there. So we've talked about a binary digit. Similarly, we've talked about instructions in here in terms of being the individual magic tricks that the CPU understands. They call them commands, but that's not very fun. So as an example, and we can even see it in this thing here, we're calling upon the MOV, the move magic trick, that's saying move this value into this location. Move this value into this location, so on and so forth. So they're calling the same move instruction over and over and over again. The example they gave us here is the add instruction. Add A plus B, storing the result back in A is typically how that instruction would end up working. But notice here the difference between this line and this line. Because we've said before, remind me, what's the difference between a high-level language, a low-level language, and a machine language?
Machine language is zeros and ones.
Zeros and ones, okay. What about a low-level language? One-to-one relationship with the CPU. So every line of code equals one magic trick on the CPU, and then a high-level language is the one-to-many. One line equals lots of those magic tricks. Okay, so ultimately, even if we're using a low-level language, some kind of assembly language, we might write an instruction like this. And that instruction ultimately then gets translated into something like this. All right, so if we look at, so this is what, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so we have 16 total bits, 2 bytes here. Now, if we assume A and B are fake registers or something like that, then we're saying that the address of B is that, 0000. The address of A is that, 1010, or the code for that is that. And then the instruction you're calling upon is that instruction. a numbered instruction on the thing. They might use less bytes, less bits than that. So it might be the instruction is actually only the first 4 bits here. And then the rest of it is, but breaking it down, I'm guessing these are nibble size registers in this example, which is, have you heard of a nibble before? A nibble is half a byte. So 4 bits. Nibble is half a byte. Okay. So assembler, this is the dude that translates our symbolic version of instruction into a binary version. So it's the tool that takes something like that a human being would be capable of writing and turns it into something like this that, yes, we are capable of it, but we would not like to do this. Okay, that's what the assembler does. A compiler translates a high-level language into something like this. That's what the compiler part does. Okay? And then the assembler turns it into the zeros and ones that your machine actually understands. So machine language then is a binary representation of those machine instructions. Make sense? All right, so this is how ultimately we go from our high-level thing down to, us writing something in Java or C# or C++ and ultimately getting it down to those zeros and ones using these power tools in between. All right, so you can go through and do, when I give you the reading assignments, you should go through and do the questions and stuff like that. I'm not going to grade you on them, or at least not on this one, and there might be some I do, but in general, I'm not going to grade you on those, but you might. So for instance, what kind of language is C? High-level language, so we should get a perfect score on that one. Haha. All right, so under the covers, that's kind of creepy. All right, so we already kind of talked about this at a certain level where we've talked about kind of the highways that live between our various components. So, this is organization of a computer. So we have our processor, we have data paths that lead to the processor, we have control structures, we have ways of getting things into the computer, we have ways of things getting out of the computer. We have benchmarks for evaluating performance, and then we have these other tools that allow us to ultimately write software that runs on this stuff. All right, so I'm going to call that relatively not that important in our big scheme of things. The idea of a data path. What is a data path based on your reading? Well, we can fill this guy out, right? Writes data to memory. Which one is this guy? This is input. All right, reads data from memory. Output. Stores instructions and data. Sends signals that determine the operation of other components. And then ultimately performs computations. That's our data path. So we can really think of our data paths as almost a formal name for a magic trick. We've referenced these magic tricks as kind of being programs built in hardware, right? You've heard me say that before. So maybe a more formal way of saying that is the data path. You enter in one side, you come out the other side, and you have your output from there for that particular piece of logic. Make some sense? All right. This gets into old display stuff. I'm not going to talk about too much of that. Pixels, this is something that is interesting for us to discuss, though. I'm going to go back over here to the slides, because this kind of goes back to our discussion last time about memory. So what is a pixel?
24-bit represent for red, green.
Okay, so it's a dot of light that has an underlying representation in memory, and if you want to use 24 bits, that's fine. So there's different memory or different graphical models we can use for representing a pixel, but 24 bits makes some sense. Okay, so we have 24 bits total for representing a single pixel. How many pixels do we have on a screen?
Resolution.
Okay, depends on our resolution. So now we have to think about screen resolution. What are some screen resolutions?
480.
So 1920 by 1080. Let's just operate off of that one. That's our what we would call standard HD. So that's your resolution for Blu-rays and that kind of stuff. Now talk is moved more towards like 4K, that kind of stuff. But 1920 by 1080, this is what you would see as 1080p on like a TV. That guy. Okay, so that means we have 1920 by 1080 total pixels. So 1920 times 1080. So that gives us this many pixels. Well, that's really annoying that you can't just click down. What's up with that? No replacement found. I don't want a replacement. All right, so that's number of individual pixels. Now, we have 24 bits per pixel. Times 24, so that gets us this number as the total number of bits. Now, if we want to get that into bytes, we have to divide that by 8. So now we're in bytes. We're going to get that into kilobytes. What do we do to it?
Divide by
1024. So divided by 1024. So that gets us kilobytes. Divided by 1024 again. That gets us megabytes. So just under 6 megabytes of data is required for a 24-bit picture on your in 1080p. Uncompressed. This is uncompressed data. But when we ultimately need to go and store it, that's the amount of data that we need for a single picture. Now, how much RAM is in our graphics cards? You go and get the latest, greatest graphics cards. They have like 11 or 12 gigabytes of RAM in them, something like that. So that's 1080 Ti has 11. The Titan X has 12. That's the differentiating factor. Otherwise, they're the same hardware inside. But regardless, they have lots of gigabytes. So how is the gigabytes in your graphics? How is that used if we only need to store 6 megabytes per picture? Well, how many frames, how many pictures do we have show up at once? Well, show up quickly. 60 a second would be considered acceptable. Probably want to have our high-end graphics cards be capable of more. So let's say that we want them to be capable of 300. Use that as so we're going to say this times 300. We're just assuming they're going to try to hit 300 frames per second as a goal. All right, so now we have that many megabytes per second. If I can divide that by 1024, now we're talking about a throughput of 1.74 gigabytes per second to get 300 frames per second on our graphics. So what do we need that 11 gigs of RAM for? What's that used for? Bragging rights? Like, look, I'm not. That actually is an interesting thing with the Galaxy Note 9. So I have the bigger one that has 8 gigs of RAM in it. So I had to get the 512 gigabyte capacity, which I didn't need that, but I wanted to get the more RAM in the phone. So my phone has 8 gigs of RAM in it, and the next one down has 6. Now, most of the time when I check, there's somewhere in the ballpark of about 2.1 gigs of RAM free. And if I free up RAM, I can get it up to like 3 gigs free. So that means that the normal version of the Note 9 is basically out of RAM at all times, or almost out of RAM at all times. What do you think?
No, it's got a small
No?
Oh, it doesn't.
No. Only difference is, in fact, it's the same machine other than the RAM and the capacity. Who would want that? Who wants a phone that's almost out of RAM all the time? So it seems like you really need the 8 because whatever Samsung's doing behind the scenes with their doctored Android, whatever is a bigger problem. Okay, but in any case, we have 1.74 gigabytes of data per second that we would need to work with to maintain 300 frames per second. What's that extra RAM used for? In order to get 300 frames per second, we need to have 300 frames ready to go within a 1 second period. So those frames need to get stacked up somewhere in memory, right? And then what about the next second? Do we have more frames for the next second? And then more frames for the next second? So the more RAM we have, assuming we have an architecture that will support this, we can have more and more of our data ready to go rather than having to be computed on the fly. And this is why when you're playing a video game or something like that, you run into an area that has a whole bunch of explosions and stuff, that things slow way down because now you're actually using the processing power of the graphics card to generate those frames. And it's taking time for them to compute it, put it into memory, and then ultimately get it out to the screen. Where the bottleneck then is the computation power of it, not the RAM. Does that make sense? So, when we deal with, when we talk about pixels, we can think about it from a performance side like this. Or going back to what you were mentioning, maybe 60 frames per second is something that we might want to have for video. Realistically, we probably can get by with 30 frames per second, but 60 is going to feel nice and smooth. So now we're going to think about this from a 60 frames per second example. So we have this many total pixels times 24 bits times 60 frames in a second. And then we're going to divide that by 8. What does not like us going that route? All right. So I'll take that, divide that by 8. That gets us that many bytes per second to maintain 60 frames a second. Divided by 1024 gets us kilobytes. Divided by 1024 gets us megabytes. All right, so now we're trying to maintain, that's total pixels, not bits. I need to go back here for a second. $207,3600. That's the number of pixels. Each pixel is going to be 24 bits, right? All right, so that's the number of bits for a single screen. Divide by 8, that's the number of bytes for a single screen. Divide by 1024, that's the number of kilobytes. Divided by 1024, that's the number of megabytes. Okay, that's for a single screen, times 60 is frames per second. So now we have 355.96 megabytes per second times 60 is number of megabytes per minute divided by 1024, 20.8 gigabytes per minute for 1080p uncompressed. What about for an hour? Times another 60?
Isn't most video like 24 frames?
It is. It is. I mentioned that before, but we want a nice and smooth video. It's going to be a big number anyway we cut it. But this is 60 frames per second. So this is for a minute of video uncompressed at 1080p at 60 frames a second. It's a lot, right? And it just gets bigger and bigger and bigger, and then we have to think about compression algorithms. How do we get this much data moving through the highways that are connecting multiple pieces? in our computer. So we have to think about things like compression versus raw data even within the paths that live inside the computer itself. So our bottlenecks inside of our computers can be all over the place. So we can kind of be impressed with what Netflix maybe does with something like this. They're doing it at 24 frames a second, but it's still, just divide this by 3, or divide it by 2.5, whatever, and it's still a big number, right? So Netflix makes it pretty impressive that you're able to watch 1080p or even 4K video at with buffering at a significantly lower data rate than this. Yeah.
So you're saying that like graphics cards tend to store these frames in their memory
because memory is fast.
Right.
So this is related to what we talked about last time, where, we can generically say that memory is fast, but at the same time, memory, there's really, 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 really fast memory, and then there's somewhat slower memory. So the RAM that's inside of our graphics cards is like DDR4 memory, the same kind of RAM that would be in our computers that we would call RAM. When you get 16 gigs of RAM in your computer, it's kind of the same stuff. So with that in mind, we data that's stored in that kind of memory is considered to be stored in a way that can quickly be transmitted someplace else, as long as the pathway between where you're transferring it to and that RAM can maintain the speed coming out of the RAM. So now you got to start thinking about the history when RAM starts getting faster. When you had a front side bus in your computer, so I'm just going to talk about it generically, of 100 megahertz, let's say. This is a long time ago. Yet you had RAM that could operate at 133 megahertz. Now all of a sudden your RAM can spit data out faster than the highway that data is going to travel on can, faster than the speed limit of that highway. So you have this great RAM, yet your motherboard, which is what's providing that highway between the RAM and your CPU, let's just say, can't keep up with what your RAM is actually capable of. So your RAM clocks down to travel slower. So you have this constant game of new hardware keeping up with other things. You go out and buy the latest, greatest DDR4, whatever gigahertz RAM, and then you put it in your machine. You might not get as much of a performance upgrade as you may have otherwise thought if you have an older motherboard that doesn't have a bus that can keep up with that speed. That's probably not a reality right now, or we're probably close to that becoming a reality maybe in a year or two. Right now, motherboard bus speeds are ahead of our RAM, but it hasn't always been that way, and it won't always be that way. Eventually, it'll catch up, and then that kind of stuff. We have this constant battle with speed and size and compression, and where do we store stuff? How fast does it need to be stored versus how much capacity do we need to store? If you start thinking about the amount of RAM in your graphics cards, we're kind of seeing an example here where storing an individual image or storing a number of images that lead up to a certain frame rate is going to start taking up a pretty big footprint of memory pretty quickly, right? If you need to hold on to the next 5 frames, let's say your graphics card is of a certain speed where if it can store 5 full frames in a row, just constantly keep that buffer filled up. It's almost like Netflix buffering your movie, right? If you can constantly keep that buffer filled up, then you'll be able to get your, pick your poison, your 300 frames per second, type thing. Not that that's the real number, just it could happen. Even though your monitor probably can't show it, it could happen. But the punchline is that graphics card has to play the game for that particular architecture where how many frames will we stack up in order to give you the best performance moving forward? Because the last thing you want to have is your graphics card's trying to pump out frames. It's going to get the next frame and there's no frame there because it's not able to keep up. So the more RAM you have in your graphics card, the more frames it can have on deck for the next view, which then buys it a little bit more time to do computations on parts of your game that are really, really, really complex. So if that particular screen is going to take more computation time than you maybe would have had between a couple of frames, you're okay as long as you had a lead of 4 or 5 frames. Kind of make some sense? and it can play the catch up after that. So that's why you have all this extra RAM on these graphics cards that, you know, help you through the tougher points in time in a game. Okay, so when we think about pixels, we want to kind of think about what the underlying, from our perspective, what the underlying memory cost might be for storing a single pixel, and how does it need to be stored? What kind of speed is it stored for? Okay. I'm not going to talk about touchscreen stuff. You can go ahead and read through that. They break down an iPad. You can read through that. We've talked about CPUs. This whole idea of a logic board, this is kind of like your motherboard, just kind of a simplified one for a you know, a smaller computer like the iPad. We talked about data paths. Really talked about all these things. We haven't actually talked about DRAM specifically, so memory built into the integrated circuit. So now we're talking about RAM that's starting to live closer to the processor, as opposed to RAM that lives kind of on the motherboard. Not that DRAM can't live on the motherboard, but typically we're talking about things inside of the processor. So notice this is kind of looks like an X-ray of a processor, right? So you're seeing, you know, multiple data paths here. So we can think of these like our, you know, these are our collection of magic tricks kind of broken up into different things. Here's our couple of cores. This is a dual core processor. So this guy, these data paths lead into these cores. You have your logic blocks. These are our various AND gates, OR gates, things like that. Got a phone call. Okay. And then ultimately, this guy is going to interface with your RAM. So this is what we're really talking about when your CPU needs to feed off of the RAM that lives on your computer, like your 16 gigs of RAM, that kind of thing. This is where it comes into the CPU. So this interface here is going to have a speed, but there's also going to be a highway. It's, you know, when you plop your processor down onto your motherboard and it has its connection pins and stuff like that, underneath the hood there's going to be a highway that's going to connect it to the various components of your computer, and one of those components is going to be your RAM. And I guarantee your CPU is faster than your RAM. So now it could deal with stuff more quickly than your RAM can spit stuff out. So now we need to have an interface for controlling how it flows in. Talked about this last time a little bit, the whole idea of cache memory being really, really, really fast, blah, blah, blah. We've talked about our instruction sets.
What about SRAM?
SRAM? Well, so go large memory with most data is stored. This is our... So what's the difference with SRAM?
It's supposedly faster than but I'm not sure what it is.
Says it uses more area to store a bit. What would the point of that be? So what we consider our normal RAM is DRAM. What we consider our small memory is cache. Okay, so now we have this guy here in the middle, which allows us to have a good amount of storage, but it actually is storing extra information about those pieces of information. Why is that? What's the advantage of maybe storing some extra data along with the data we already have? Go ahead.
Allowing for identification.
So almost think about this from like a strongly typed versus loosely typed language. When we have a loosely typed language, we have type inference engines that have to kind of gaze down and figure out what kind of value lives inside of this bucket. If we can store extra information about individual bits, we can make decisions about some things more quickly. This goes back to our first screen 8 Great Ideas, where we talk about prediction versus wherever it was, performance via prediction. Okay, sometimes we can get additional information out of those bits before we need to use the data. That was still under the covers, right? All right, so this binary interface, this is kind of a subset of our instruction set. Just think about things in terms of our instruction set. These are all of the instructions that a CPU has. Otherwise, we're thinking about things in terms of this is an Intel-based CPU. Intel-based CPUs are going to work on machines across large periods of time. So this year's architecture is still backwards compatible with last year's architecture up to a point. You might have a motherboard that's old enough that it can't take at certain socket size. You might have usually you'll see the socket sizes actually change or the socket names change when you can no longer use the processor in an older board. So when you buy a motherboard, it'll say this supports socket XYZ. And you might have 3 or 4 different generations of a processor that fit in socket XYZ. Those should all work on that particular motherboard. Not until they make a major change in the architecture do you then have to probably have a new socket size or socket name. It might not be physically a different size, but it might have a different number of pinouts or different pattern of pinouts, whatever it is, that says your old motherboard won't run this new processor because it doesn't have the connectivity for it. So they're saying application binary interface, the user portion of the instruction set. So this is really where it connects directly into the operating system for compatibility across multiple platforms. I don't know that you want to have a distinguish. I don't know that you want to distinguish between operating system specific instructions versus normal generic instructions. Because you can have an Intel Core i7 processor that runs on the Mac, that runs on the PC, that runs on, on Linux, and they might have some things built into it that make it perform certain tasks, certain magic tricks that are OS specific. Just because they had room for it, and that's where that thing is typically used, things like that. So I would just think of things generically as the instruction set. We talked about this a little bit when we were mentioning the different kinds of memory. We have volatile memory versus non-volatile memory. So non-volatile memory is memory that retains its stuff over time. So when you turn your computer off, it goes away, or it stays there rather. Whereas volatile memory, it goes away. So the way our RAM chips work in our computer is when the electricity is on, it's kind of maintaining all the stuff in memory and holding it there. All right, and then once we turn the power off, it goes away. So if you think about your laptops these days, when you shut the screen and it kind of goes into the hibernation mode, what it's doing is it's copying a bunch of the stuff that's currently in RAM to the hard drive so that next time you open the lid, it can wake up and load that stuff back into memory and pick up where it left off. Because your memory itself, your RAM in your computer itself, is not capable of storing that stuff when you have electricity turned off. Does that make sense? It's the nature of how that memory works. Don't care about that stuff. All right. Now we're getting into some of the more interesting parts of this. We mentioned vacuum tubes and transistors a little bit last time. This gives us a kind of an interesting comparison of performance relative to the cost per unit. Now, cost per unit over time has changed because the technology used to be a lot more expensive for a single transistor when it first came out than it is today, but we can at least see the scaling factor. So back in the early days with vacuum tubes, and let me bring up a picture of maybe UNIVAC. Maybe something you saw in like a 150 class or something like that. So something like this was a computer, that was not anywhere near as powerful as what you have sitting in front of you right now, even if it's just your smartphone. So I'm going to just do a search for vacuum tube. You see it kind of looks like a light bulby looking thing. Yeah, this is good enough one. All right, so when you're storing data in a computer based on vacuum tubes, on or off is relative to a 0 or a 1, right? So you have to go through and you turn lights on and off depending on what the current representation is. Now, the very early ones, you would actually, screw in the bulb or or turn it off. Otherwise, you would apply electricity to it, or there would be an individual switch. But what we think of as a transistor, which is effectively a built-in switch for either allowing electricity through or not allowing it through, you would actually have a physical switch to switch a bulb on or switch a bulb off. So when you consider just that's why these machines are so large. The more stuff you needed to be able to store, the more vacuum tubes you needed, the more physical space you actually needed. So now you have a whole gymnasium filled up with a computer that couldn't even power a toaster today. Some of our smart toasters are quite a bit of stuff behind them. All right, so
Smart toasters.
oh yeah, oh you know about this from the Internet of Things, IoTs.
Oh, yeah.
Oh yeah, you could upload a picture and have them print out Yoda toast.
Sorry, for some reason I was thinking of tweeting from the side of the toaster.
Tweeting from the
I've seen like dishwashers and
I get what you're saying.
that have Twitter on them. So I'm like, toasters have that now too?
Well, what happens when we start having AI and stuff built into our toasters, where our toasters start to get to know us, and then all of a sudden our toaster becomes a little bit too human and starts sending us messages in the middle of the night. I'm cold. I'm lonely.
You're just gonna build a camera inside your toaster so you can put it up on your phone and tell it done toasting.
And then you have to have a robot to get the toaster, get the toast and bring it to you. But yeah, there's already toasters where you can put an SD card in there and it'll print onto your toast the image. It'll burn onto your toast the image that you wanted, so you can make Yoda toast. Makes sense, doesn't it? Who wouldn't want Yoda toast? All right, so in any case, vacuum tubes, big and slow by today's standards, but allowed us to do computing when we couldn't do it otherwise. And let me show you a picture of a transistor. All right, so these are actually getting to some of our newer style transistors. Let's see if we can find a relatively old one, but no, this is good enough. It'll be good enough for this example. All right, so a transistor works as a switch. This is the actual logic inside of here. So we have 3 inputs. Well, you have 2 inputs and 1 output, but the output acts as an input and an output because that's how the switch works, and we'll talk about that. But punchline is this is a lot smaller than smaller than a light bulb, but still has a physical size to it. Like here's one next to, I don't know what that is, like a little button snap or like a battery or something. There's a physical size to that, right? It's something like this. Smaller than a vacuum tube, but still has a size. So when we go back here, we talk about that, they say a transistor effectively had if we just want to compare this in size, it was 35 times smaller than a vacuum tube. Fair enough. Okay. Well, then we start getting into this idea of an integrated circuit. So now we have what we start thinking of as our modern day CPUs. Or the data paths on the CPU, where we can now squeeze a whole bunch of things into a much smaller space. So now that is 900 times. They're doing it relative performance, but maybe we could just do it based on size. If we assume that a switch has a performance associated with it, regardless of the how quick the highways are behind it, because these are fast. This is just a wire that's sitting behind this thing, that for every 35 transistors, we could have 900 integrated circuits, something like that. So we certainly see things big build up. Now we have this thing, VLSI, very large scale integration. So now we've gotten better. Notice this is 1975 is when we had the original integrated circuits. 1995 is when we made the jump to large scale integrated circuits. Now, I'm not saying go back all the way to 1975, but I've referenced a couple of computers in here from the kind of the mid to late 90s. I think I mentioned that I had like a 486 DX2 66 megahertz computer, and that was somewhere in like the 1995 range. So, right towards the end, let's say, of the normal integrated circuit. So the biggest evolution of that, but before we had machines shipping with the VLSI. So one thing you would have seen between maybe 1996 and 2000, let's say, is you would have seen a really quick jump in processing power, substantially so. So you would have seen, so like I said, in 1995, I had a 66 megahertz processor, and in 1999, there were at least 400 megahertz processors, I think. So I think I told the story about the guy in the dorms with the Celeron. I think it was a 233 megahertz Celeron. He overclocked to a gigahertz or something like that, and lit up. Okay. But in any case, we saw a giant jump when we had this line in the sand between we can only get things so fast right here, and then we can only get things so fast right here. 2013, we had ultra large scale integrated circuits, and notice the jump right there. So this was new technology for printing circuit boards. Now, since 2013 to today, have we seen drastic jumps in processor speed? No. Why not? No, this says we can squeeze a lot more. We got a lot more. We can make all the things that used to be small, we can make them even smaller, a lot smaller.
There's a law that's actually preventing us. I can't remember someone's law.
About Moore's law? And Moore's law tells us what we can expect to happen. But what have we noticed that's really happened since 2013 to today in terms of our processors? Has the clock speed gotten faster? No. What has gotten bigger? Number of cores. Yeah, so clock speed hasn't gotten faster because of heat. Okay, sure, you can squeeze more stuff in that space. It's just going to cause more heat, and your machine is still going to melt. Okay, so we can't. I mean, you could put all this dynamic cooling stuff in there until you. We even had this issue recently with Apple. Apple came out with their latest high-end MacBook Pro that had an Intel Core i9 processor in it, which is Intel's highest end processor right now. And well, Apple kind of prides itself in its machines not having too many moving parts and everything being super thin and stuff like that. So, if you put something that's giving off that much heat into that kind of space, it's bad. So Apple throttled the processor and then got caught, and now has had to unthrottle the processor through a software patch. But now they got to play this game where when do I throttle it up to get you some performance versus when do I throttle it down so your laptop doesn't give you 9th degree burns in your legs, something like that. I just invented 9th degree burns, so it's they're bad. All right, it's a really bad thing. You don't want to have that. But in any case, we really haven't had processors get faster in recent years. Instead, we've seen more cores because we're able to put more stuff with the same number of matrix or similar number of matrix onto the same die. And we'll see that in the, actually it's probably later on in this processor thing when we talk about silicon dies and things like that. But in any case, we are getting pretty good at making things smaller and smaller and smaller, but that's not really helping us anymore. We're kind of getting diminishing returns because we've already talked about this idea of whether or not more cores is always better than less cores. Fine, you can put 1,000 cores into a processor. You're probably only going to use 3 or 4 of them or 5 of them at once. Did I really need to pay for the 1,000 cores? Well, the super users are going to say, well, yeah. Because it makes your machine sound better than it would have been otherwise. But from a practicality perspective, you're not really going to use it. All right, so at some point in here, we're probably going to see a major jump. We saw a jump, in the late 50s. We saw a jump in the late 60s. We saw a jump in the late 70s. Then late 90s, we saw a pretty big jump. This was probably the point in time where we saw, from a human measurement perspective, the largest jump in our processing power because so many people knew about computers. So when you walked into Best Buy one day and then you went there 2 months later, you saw processor speeds that were triple what they were a month or two ago from this leap right here. This more recent one, we probably didn't even know happened because we're still fighting the heat battle. Okay? So transistor, as we've advertised, is an on-off switch, but it's controlled by an electrical signal rather than a twist or flip switch on and off. So not light bulb thing. Very large scale integrated circuit, device containing hundreds of thousands to millions of transistors. So we saw a picture over here of one of these dudes, right? So now we're going to have technology that squeezes them down to this tiny, 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 tiny level, and then we're going to put a whole bunch of them in a very small space. These are not handcrafted anymore. Yeah, you know, some guy whittling very large scale integrated circuits out of. He's sitting there with a soldering iron, and he's got the tweezers.
He's got the little pick and the block of silicon.
Yeah, it's not happening. Yeah, we have machines that are doing this, which actually then leads us kind of something that we're going to talk about here in a little bit that talks about the failure rate. And this is one of the reasons why, well, when I get to it, I'll talk more, but one of the reasons why really PowerPC probably fell apart is they were having a high failure rate in the creation of their dies. All right, so that's transistors. Now we start looking at RAM over the years. RAM is made up of transistors as well. All right. We're storing a whole bunch of on and offs, zeros and ones. That's our capacity. So the more transistors we can fit into the same spot, the more memory we can have. And when we provide power to that RAM, we are that's what's holding it, in its static state. And as soon as we drain electricity, it forgets everything it currently had. And that's why when you shut your laptop lid and it hibernates, it has to go into something else. Okay, but if we look at over the time, this is a good way of kind of visualizing how our RAM has gotten larger and larger capacities. So look back out here, back here in the late 70s, what was considered a lot of RAM was 16 kilobytes of RAM. It's a lot of nothing by today's standards, right? Okay, and what was I think Bill Gates' famous line, you'll never need more than 32K of RAM or something like that. I think he said something like that. Maybe it was 64K, whatever his quote was. Somewhere right in this ballpark. It's right around this time he said that. So in 80, we had 64K of RAM. In 84, a megabyte. In 1990, late 80s, 4 megabytes. My machine, I don't even know if this isn't... I question the full accuracy of this.
640K.
It was 640K, you said?
Mm-hmm.
In 1995, right around in here, that computer I mentioned, the 486DX2 66 megahertz, shipped with 8 megabytes of RAM. And that was considered a lot of RAM in a personal computer then. So they're listing 16 megabytes in 1992.
Well, that's the year of introduction.
Yeah, maybe it was just too expensive.
Yeah, I mean,
which would make sense, yeah.
64 in 1980. You didn't really see 64K until maybe 84.
All right, so in 2012, we had a 4 gigabyte chip. 4 gigabyte chip. Then obviously now we have 8, we have 16 gigabyte and 32 gigabyte chips. I think there are 64 gigabyte chips that Samsung has announced. I don't know that you can buy them yet, but they're a thing. And I'm sure there's some custom company out there that'll just make you whatever chip you want. If you'll write them a check and you don't have a form factor that you have to fit, if everything just be soldered. All right, so in any case, we've seen kind of the evolution of that. So this next thing, dealing with silicon and this idea of a semiconductor. So what's a conductor? What does it mean for something to be a conductor?
Makes music.
Yeah, that guy.
That's what I'm saying,
Okay.
we'll place it
Okay.
on it.
So go ahead.
Allows the electricity to pass through.
Without too much resistance, right? It's a good conductor would be something where if you put your finger on one side and you put electricity on the other side, it would be bad. Okay, that's a good conductor, unless you've grounded yourself, I suppose. But a semiconductor, as its name indicates, is kind of good at conducting. Okay, it doesn't just let free flow, but it doesn't block. It's not overly resistant. So this is a substance that does not conduct electricity well, but it does conduct electricity. All right, and silicon, which is what most of our hardware components are made of these days, is a natural element that acts like this. So we have some control over it rather than everything moving at the speed of light, where we might not have time to make decisions. Make some sense? Okay. All right, so all these things are created from this ingot. So you think it's like a tube looking thing that they cut little slices off of when they're making their processors. So it's like, I don't know, like Play-Doh or something like that. So a rod composed of silicon crystal is between 8 and 12 inches in diameter and about 12 to 24 inches long. Oh yeah, I did. Okay, so then we have this thing called the wafer. This is all talking about how processes are made. So a wafer is a single slice from this. Notice it's no more than 0.1 inches thick, and it's used to create our processors, our chips. All right, and they kind of show what this process looks like. So we start with our ingot, goes through the slicer. Slicer creates these little blank wafers. It does a whole bunch of stuff, ultimately putting grids on these wafers. So we have this patterned wafer. Goes farther than that, doesn't it?
You have to hit the little play button.
Oh, I have to go next step. All right, so now we're testing the integrity of the wafer itself. We haven't even started putting stuff onto it yet. So there is a point of failure that goes there, that happens there. All right, so now we break these guys into individual dies. So now we've referenced the idea of a die in here in terms of kind of almost like the core. So if you have a quad core processor, there would be 4 individual dies on that processor. That's not 100% true now. The way they construct them to try to this is kind of where the turbo thing comes from, to allow you to go higher clock speeds. They do a little bit more insulation between the dies, but it's still a fair enough, I think, assumption. So once they've said, okay, this wafer is good, we're going to go ahead and chop it up into individual dies on which we're going to actually build our data paths. All right, so this is our package die. So somewhere in here is where the data paths are kind of created in that guy. So this is what we build our processors on top of. So this whole idea of defects, this was something that was a pretty big problem with IBM and the PowerPC processor in the early 2000s. A microscopic flaw in the wafer or patterning steps that can result in the failure of the die containing the defect. I don't remember the exact numbers, but there was a pretty high rate of defects for the PowerPC G4 processor that IBM was creating, and that probably forced Apple to look pretty seriously at switching to Intel. It's probably a pretty big part of it. And that kind of leads to this yield. So their yield was not very good for those PowerPC processors. They had a lot of dies, and only a small percentage of them were actually viable. All right. Performance. So this is the stuff we're going to start looking at. So I'll have you for next time read a little bit more. But I'm going to start looking at this for a few minutes. So let's see. We're going to go through that. Definitely want to talk about multiprocessors. Yeah, I think through 1.10 would be good for next class. 1.6 to 1.10. Now, there are exercises at the end of this chapter, and I want to give you some of them for Tuesday, but not too many. Let me just see what they're talking about in here. Yeah, I don't want to talk about that stuff today. That's just math dealing with that. All right. So let's see exercises. I want to ask reasonable questions, not just time waster questions. All right, so let's do so we are going to do 1.3. That looks like a good one. We are going to do 1.4. That's similar to some of the math we did today. Not that. Yeah, just those. The next ones I would do is from the next section. All right, so let's look ahead here a little bit. All right, so 1.6 and 1.7 are going to deal with us doing some mathy stuff related to processors. At least 1.6 was that. This is still... Oh, this is getting into the whole idea of why we have kind of hit the wall and we've started switching over to multi-core. So that's going to be that guy. We've talked about some multiprocessor stuff, so this is going to be a pretty interesting section. Benchmarking we'll probably look at just for a few minutes. All right, so that'll get us through, so probably by next Thursday, I would think, we'll be through the end of chapter 1, and then we can start getting into our ARM instruction set. So this is when we'll start looking at, and there's a built-in ARM simulator in here as well that we can use. But this is when we'll start doing the assembly stuff. So probably a week from Tuesday, would be my guess, is when we're going to start the assembly language stuff. Okay, questions, comments, concerns, bribes. All right, make sure you complete the Bible homework for Sunday by midnight. Make sure you complete this assignment for Tuesday by 1 p.m. And I will see everybody on Tuesday.